concept related to this question are the variation of pressure with depth. What we have here is an object suspended in water between position X and Y, and the volume of the water is in equilibrium. The region has an area of A, and the external forces acting upon it are the gravitational force, mg, the upward force, P2A, and the normal downward force, P1A. The sum of these forces would be 0 as they are in equilibrium. The net force shall be 0. Thus, P2A minus P1A minus mg is equal to 0. The reason why I subtract P1A and mg is that P1A and mg are a downward force, but P2A is an upward force. The m from mg could be calculated by multiplying it with its density and volume, where volume could be calculated from area times by its height, which over here is x minus y. Thus, cancelling the area, and reshuffling the equation to obtain the upward force, we will get the upward pressure P2 is equal to P1 plus rho G x minus y. Relating it to the said question, we are calculating the upward pressure exerted onto the oxygen tank below the height h. Relating it to the formula that I derived above here, to find this P, it would be PO plus rho GH, where P1 at a depth below H below the surface of a liquid exposed to the atmosphere is larger than the atmospheric pressure by rho GH. And the atmospheric pressure is 1.013 times by 10 to the power of 5 Pascal at sea level. The second concept relating to this question is the ideal gas law. The ideal gas law basically combines the three different gas laws, which are Boyle's law, where pressure is inversely proportional to volume, Charles' law, where volume is directly proportional to temperature, and Gay-Lussac's law, where pressure is directly proportional to temperature. This formula basically explains that pressure times by volume is equal to nRT, where N is the number of moles, R is the universal gas constant, where R is equal to 8.31 joules per mole Kelvin, or 0.0821 liter ATM per mole Kelvin. And T is the temperature in Kelvin.